Mission planners, I find, must reconcile the search for an ideal observational window with Mars's unpredictable atmospheric conditions, which might compromise the quality of our data. The timeline for data retrieval adds another layer of complexity. Martian orbiters typically transmit their collected information to Earth during pre-scheduled communication windows, and these periods may not align perfectly with the brief encounter. Consequently, I know some of the most compelling findings might not reach Earth for several days or weeks after the fact, hindering our ability to arrange subsequent investigations or share preliminary findings with the global astronomical community. Notwithstanding these obstacles, the Mars flyby represents our best opportunity to witness this interstellar visitor during its peak activity. Soon, I realize, terrestrial telescopes will no longer be able to track 3I Atlas as it becomes lost in the Sun's brilliance, making the Martian observations possibly our last clear view of the object until it reappears from behind the Sun months later, assuming it survives the passage at all. The scientific insights procured from these observations could provide critical confirmation for competing theories about the composition of 3I Atlas. Natural comets subjected to thermal stress near the Sun should display predictable patterns of dust and gas release, observable as changes in the coma's luminosity and the structure of its tail. Any significant deviations from these expected patterns might suggest more unconventional explanations for the visitor's behavior. It is vital, however, to maintain realistic expectations regarding what these observations can and cannot reveal. The Mars flyby does not involve any direct physical contact or a close-quarters approach. The object will remain millions of kilometers away throughout the encounter. We will collect no samples. We will resolve no surface features, nor will we obtain detailed information about its inner structure. This observation effort also serves as a proof of concept for future investigations of interstellar objects. The techniques developed and confirmed during the 3I Atlas Mars flyby could inform observation strategies for subsequent visitors, potentially leading to more sophisticated and coordinated international campaigns to examine these rare cosmic travelers. We have contingency plans that address the potential for technical failures, communication breakdowns, or poor viewing geometries to reduce or even nullify the acquisition of useful data from the flyby. Backup observation strategies utilizing Earth-based telescopes provide a measure of redundancy, though they are increasingly compromised by solar glare and atmospheric interference as the encounter approaches. The schedule for the Martian encounter compresses the most scientifically valuable observational opportunity into a span of just a few hours or days centered around the moment of closest approach. During this brief window, our robotic representatives orbiting the red planet will turn their electronic senses toward a traveler from another star system, aiming to capture whatever truths it might disclose as it passes through our corner of the cosmos. If Mars could tune into the electromagnetic spectrum during those crucial hours, I wonder what stories it might discern amidst the background noise of space. The instruments will listen with the patience of machines and the curiosity of their human creators, hoping to translate any signals that might be written in the light of a stellar wanderer. But first, the visitor must keep its rendezvous with our solar system's fourth world, carrying its mysteries past the watchful gaze of our Martian sentinels on its journey to its ultimate fate behind the blinding light of our Sun. Part 9. Swan, R2. The New Giant. Just as 3I Atlas commanded attention as an anomalous traveler from beyond our solar system, another celestial nomad was quietly preparing to claim the spotlight. Comet C 2025 R2, better known as Swan R2, after its discovery and data from the Solar and Heliospheric Observatory, emerged from the distant frontiers of our own solar system, developing into one of the most stunning cometary displays witnessed from Earth in recent memory. The story of its discovery begins with the unwavering dedication of amateur astronomer Vladimir Bazugi, who poured countless hours into examining images from the Swan instrument, looking for the telltale signatures of new comets hidden in the Sun's glare. On the 11th of September 2025, his perseverance paid off when he detected an anomalous brightening in the data, which was soon confirmed as a previously unknown comet approaching its closest pass to the Sun. The SWAN instrument, which stands for Solar Wind Anisotropies, on the SOHO spacecraft, is an unlikely tool for discovering comets, as it was primarily designed to observe solar wind interactions with the interplanetary medium. By mapping the distribution of hydrogen atoms created when solar ultraviolet radiation breaks apart water molecules, SWAN can detect cometary activity that is invisible to conventional telescopes, particularly for objects located too close to the Sun for safe ground-based observation. The appearance of SWAN R2 from behind the Sun underscores a fundamental challenge in comet detection. Long-period comets often spend months approaching the Sun from perspectives that place them at a minimal angular separation from our star as seen from Earth. The Holetschek effect, named for the Austrian astronomer who first described it, explains why many bright comets appear to burst into our skies suddenly, fully formed and already active. The comet's official designation, C 2025 R2, conforms to the established naming conventions of the International Astronomical Union. The C indicates a long-period comet, likely originating from the distant Oort cloud that surrounds our solar system. The year 2025 marks its discovery year, and R2 signifies it was the second comet discovered in the second half of September. By mid-September 2025, SWAN R2 had already become perceptible without optical aid to observers in dark sky locations, shining at roughly 6th magnitude, the threshold for naked-eye visibility under ideal conditions. Yet, unlike many comets that brighten to a peak and then fade, this visitor continued to increase in luminosity as it receded from its solar encounter and moved toward its closest approach to Earth. The astronomy picture of the day for September 16th featured SWAN R2 as a newly discovered comet, visible with binoculars, noting its rapid brightening and the impressive tail development that was making it a favorite target for astrophotographers worldwide. The comet's position near the bright star Spica in the constellation Virgo provided a convenient reference point for amateur astronomers seeking to locate it in the evening twilight. Reports from experienced comet watchers began to document tail lengths extending up to 2 degrees across the sky, which is about 4 times the apparent diameter of the full moon. These estimates, though imprecise due to the subjective nature of visual comet observation and the image processing techniques used, suggested a tail structure spanning millions of kilometers in actual distance. The comet's orbital parameters tell the story of a visitor from the far reaches of our own solar system. Unlike 3I Atlas with its hyperbolic interstellar trajectory, SWAN R2 follows a highly elongated ellipse that carries it from the frozen realm beyond Neptune's orbit to a point within 0.5 astronomical units of the Sun. This is a journey that takes decades or centuries, during which the comet remained frozen and inactive until the Sun's heat triggered the spectacular display we are now observing. Perihelion occurred on September 12, 2025, when SWAN R2 made its closest pass to the Sun at approximately 0.5 astronomical units, about half the distance from Earth to our star. This close solar encounter subjected the comet to intense heat, vaporizing surface ices and liberating the dust and gas that create the visible coma and tail. The comet's closest approach to Earth is projected for October 21, 2025, when it will pass within 0.27 astronomical units of our world, roughly 40 million kilometers away. This creates a favorable viewing geometry that makes SWAN R2 an excellent subject for detailed study during the same period that 3I Atlas is approaching its own perihelion. Current brightness forecasts place SWAN R2 at a magnitude of 6 to 7 in mid-September, making it easily observable with binoculars and on the verge of naked-eye visibility for observers with excellent viewing conditions. Its ongoing brightening suggests the comet could reach a magnitude of 4 or 5 by its closest approach to Earth, potentially making it one of the most brilliant comets of 2025. The southern hemisphere has the most favorable viewing conditions for Swan R2 during its evening appearance, though observers in the northern hemisphere can still catch the comet low in the western sky after sunset. The comet's orientation relative to the ecliptic plane and its motion with respect to Earth create changing viewing perspectives that affect its visibility throughout its apparition. Networks of amateur astronomers worldwide have mobilized to document the evolution of Swan R2, creating a real-time observational archive that supplements professional astronomical studies. High-quality images from expert comet photographers reveal intricate details in the tail structure, including potential disconnection events where interactions with magnetic fields cause sections of the ion tail to temporarily break away from the comet's main body. Nevertheless, significant uncertainty remains about the orbital parameters of Swan R2 due to the relatively short observational arc since its discovery. Comets can be influenced by non-gravitational forces from outgassing that subtly alter their trajectories, making precise long-term predictions challenging until more observational data is collected. The Minor Planet Center is continuously updating the orbital solutions as new astrometric measurements arrive from observatories across the globe. These calculations will eventually determine whether Swan R2 follows a closed elliptical path that will one day bring it back to the inner solar system, or if gravitational perturbations during this pass will eject it permanently into interstellar space. Hazard assessments indicate that Swan R2's current trajectory presents no threat to Earth. The closest approach distance of 0.27 astronomical units offers a wide safety margin while providing outstanding opportunities for detailed study of this visitor from the outer solar system. Standard protocols are in effect to monitor the comet's trajectory for any unexpected changes that might alter these predictions. The comet's rapid development and spectacular appearance have turned it into a major subject for public outreach and educational initiatives. Astronomy clubs and planetariums worldwide are featuring Swan R2 in their programs, using its visibility to educate the public about comet composition, solar system architecture, and the dynamic processes that shape our cosmic environment. Professional observatories are beginning to allocate time for spectroscopic and photometric studies of Swan R2. While the majority of telescope resources remain focused on 3I Atlas due to its exotic interstellar origin, Swan R2 provides invaluable opportunities to study the composition and behavior of objects from the outer regions of our own solar system. The timing of Swan R2's appearance, occurring almost simultaneously with 3I Atlas's passage through our inner solar system, creates a rare opportunity for comparative studies. Two fundamentally different types of objects, one from interstellar space and one from our own Oort cloud, are undergoing similar physical processes under comparable solar heating, allowing scientists to investigate how their formation histories affect cometary activity. If 3I Atlas is a scout exploring our cosmic neighborhood, I have to ask why Swan R2 arrives like a city-sized harbinger of something far more significant. The cosmos rarely provides such convenient juxtapositions for comparative study, making October of 2025 a month that could redefine our understanding of what travels through the voids between and within star systems. Part 10. Technical Speculations, Engines, Shields, and Orbits. In the realm of theoretical astronomy, the line between the anomalous and the artificial often becomes blurry, where unusual observations can ignite extraordinary theories about what might be possible in a universe filled with intelligence we have yet to meet. 3I Atlas and Swan R, two display characteristics that, while explainable through natural processes, also invite me to consider more audacious possibilities, if only as thought experiments in the physics of controlled propulsion and directed energy. First, I consider the question of propulsion. Natural comets follow paths dictated entirely by gravitational forces, their trajectories through space determined by the inverse square law, and the initial conditions of their formation or ejection from distant star systems. A genuine propulsion system would be detectable through observed deviations from these expected orbits, such as sustained acceleration vectors, attitude adjustments, or course corrections that violate the principles of ballistic motion. A directed plasma drive operating by ejecting ionized gas at high velocities would leave signature evidence in both the trajectory and the electromagnetic spectrum of the object it propels. The exhaust plume would radiate light at specific frequencies, determined by the composition and temperature of the expelled material. More importantly, the thrust vector would induce noticeable changes in orbital elements that would, over time, accumulate into clear violations of Keplerian motion. 3I Atlas exhibits none of these indicators. Its hyperbolic trajectory is consistent with an object unbound to our Sun, and its brightness and spectral changes correlate predictably with its decreasing distance from the Sun. The outgassing observed by our most sensitive instruments appears to be perfectly consistent with natural sublimation processes driven by solar heating. Yet the precision of its timing, arriving in the vicinity of Mars and Earth in a tight window that coincides with Swan R2's close approaches, challenges statistical probability in ways that keep speculative theories alive. If this convergence is coordinated rather than coincidental, it would require propulsion systems that operate with a subtlety that renders them invisible to our current detection methods. Electromagnetic shielding represents another area where natural processes might be masking artificial operations. Comets naturally develop plasma sheaths as the solar wind interacts with the ionized gas in their expanding comas. These interactions create complex magnetic field structures that deflect charged particles and dictate the characteristic antisolar alignment of ion tails. An active electromagnetic field system could mimic these natural plasma interactions, differing only in the degree of control and directionality it might exert on the local charged particle environment. The key distinction would lie in identifying field geometries that serve no apparent natural function, magnetic configurations designed for communication, energy collection, or radiation shielding, rather than the simple diversion of the solar wind. Current observations reveal ion tails that behave exactly as predicted by natural interactions between a comet and the solar wind. The James Webb Space Telescope and ground-based spectrographs have detected no anomalous electromagnetic signals, no coherent radio bursts, and no evidence of controlled field manipulation beyond what the physics of the solar wind naturally induces around active comets. The orbital dynamics of deliberate patrol patterns would require recurring visits or systematic area sweeps that would distinguish artificial trajectories from the random encounters expected of natural interstellar objects. Long-period comets from our own Oort cloud can appear as one-time visitors even when on closed elliptical orbits, as their periods often exceed the entire span of recorded human history. True patrol behavior would eventually reveal itself through repeated apparitions at regular intervals, synchronized arrivals of multiple objects, or trajectory adjustments that serve strategic rather than purely gravitational purposes. The 3 confirmed interstellar objects detected since 2017, 1I Oumuamua, 2I Borisov, and now 3I Atlas, show no signs of systematic organization or coordinated movement. Avi Loeb's theory of a response to our transmissions provides a fascinating thought experiment on the possibility that our electromagnetic leakage into space might have triggered automated responses from dormant surveillance systems distributed throughout our local galactic neighborhood. This hypothesis would explain the apparent temporal correlation between our technological advancement and the arrival of unusual visitors. However, NASA and ESA maintain that the current observational evidence remains consistent with natural origins, despite the object's peculiar characteristics. The agencies emphasize that extraordinary claims require extraordinary evidence, and the chemical signatures, orbital dynamics, and physical behavior observed in both 3I Atlas and Swan 2 fall within the spectrum of natural cometary activity, albeit at the more exotic end of that spectrum. The detection of nickel without iron in the spectrum of 3I Atlas illustrates how an unusual chemical composition can be interpreted through both natural and artificial lenses. Industrial processes could selectively concentrate certain elements or isotopes, leaving distinctive fingerprints in the resulting exhaust or waste products. But the SETI analysis offers a detailed discussion of natural processes, nickel-carbonyl chemistry, space weathering effects, and selective sublimation that could produce similar chemical signatures without invoking technological origins. Color changes and switching on behaviors represent another domain where natural and artificial hypotheses compete for explanatory power. Comets frequently exhibit nonlinear brightening curves as different volatile compounds reach their sublimation temperatures at varying distances from the Sun. This creates the appearance of discrete activation events that could be misconstrued as propulsion systems coming online, when they are, in fact, a reflection of the physics of ice vaporization in a vacuum. To distinguish between natural outgassing and engineered emissions, one must identify thrust vectors, acceleration profiles, and energy budgets that exceed what random sublimation could produce. Current observations indicate that brightness and spectral changes correlate precisely with the expected behavior of sublimating ices under increasing solar insolation. The hypothetical signatures of genuine engineering would be observable through multiple observational channels. A sustained thrust acceleration would, over time, produce detectable orbital perturbations. Attitude control systems would induce periodic variations in brightness or spectral characteristics as different faces of the object rotated toward or away from the Sun. Coherent electromagnetic signals would stand out against the natural radio background of space. Coordinated international monitoring campaigns have been searching for precisely these types of anomalous signals using radio telescopes, radar facilities, and sensitive photometric instruments. The Very Large Array, the successors to Arecibo, and other major radio observatories have conducted systematic scans for artificial signals from both visitors. No coherent transmissions, no structured electromagnetic emissions, and no evidence of active electronics have been detected. Radar observations by multiple facilities have also come up empty, though the immense distances involved make detection challenging even for the most powerful planetary radar systems. The absence of strong radar returns is consistent with natural cometary surfaces composed of low-density ice and dust rather than metallic or highly reflective artificial structures. Infrared observations provide another avenue for distinguishing between artificial and natural origins. Spacecraft or manufactured objects typically possess thermal signatures that differ from natural bodies due to their internal power sources, thermal regulation systems, or exotic materials. Both 3I Atlas and Swan 2 display infrared emission profiles consistent with the solar heating of natural assemblages of ice and dust. The energy budgets implied by various technological scenarios also become implausible under quantitative scrutiny. Interstellar travel requires vast quantities of energy, whether for propulsion, life support, or communication across galactic distances. Objects capable of such feats would presumably show evidence of advanced energy systems, which are conspicuously absent from our observations. There exist mission escalation protocols within the international astronomical community for responding to genuinely anomalous discoveries. If multiple independent observatories were to detect unambiguous signs of artificiality, structured signals, non-gravitational acceleration patterns, or impossible chemical compositions, coordinated follow-up campaigns would mobilize resources from NASA, ESA, and other space agencies for intensive investigation. These protocols have not been activated for either 3I Atlas or Swan 2, indicating that despite their unusual properties, both objects are still considered within the realm of natural phenomena by mainstream astronomy. The scientific consensus continues to favor exotic but natural explanations for their observed behaviors. However, the absence of detected artificial signals does not conclusively prove a natural origin, especially for hypothetical technologies that operate beyond our current detection capabilities. Advanced civilizations might employ propulsion systems, communication methods, or material science that produce signatures we are not yet equipped to recognize or interpret. This epistemological limitation, our inability to definitively rule out artificial attributes, creates space for continued speculation about technological interpretations. The gap between what we can observe and what might theoretically exist allows for scenarios that cannot be falsified with our current instrumentation. The psychological appeal of technological explanations arises from deeper human needs to see intention and intelligence in natural events that might otherwise be simple coincidences. The precise timing of the arrivals of both visitors, their peculiar properties, and their convergence in our solar system during a period of human technological ascendancy create narrative patterns that our pattern-seeking brains interpret as potentially meaningful. Statistical analysis of the arrival rates of interstellar objects suggests that the apparent clustering of unusual objects in recent years may be an observational selection effect rather than a true increase in the visitation rate. Our detection capabilities have improved dramatically over the last decade, making it more likely that we would notice objects that might have passed undetected in previous eras. The 3 confirmed interstellar objects discovered since 2017, 1I Oumuamua, 2I Borisov, and 3I Atlas, each possessed characteristics that initially baffled scientists but were eventually explained through natural processes after intensive study. This history suggests that unusual properties do not necessarily imply artificial origins, even when those properties challenge existing theoretical models. Computer simulations of interstellar object trajectories indicate that our solar system should receive natural visitors at rates roughly consistent with current observations, given plausible assumptions about the population density of ejected bodies in our local galactic neighborhood. The timing and characteristics of recent visitors fall within the expected distribution for natural interstellar wanderers. Yet the possibility remains that some fraction of detected interstellar objects might be technology so advanced that it perfectly mimics natural phenomena, either by design or as an unavoidable consequence of advanced engineering that operates in concert with, rather than in opposition to, natural physical principles. Such technology would be nearly indistinguishable from natural objects using our current observational methods. The definitive test of these competing hypotheses may come during the October solar encounters, when both visitors will experience their most intense heating and may reveal characteristics that were concealed during their cooler approach. If artificial systems are present, the stress of perihelion passage could induce responses or failures that would distinguish them from purely natural behavior. Ground-based telescopes will be unable to observe both objects during their closest approaches to the Sun, creating an observational blackout during the most scientifically critical period. This gap in our coverage means that the most definitive evidence for or against technological explanations might emerge precisely when we are unable to see it. Observations from Mars during the October 3rd flyby of 3I Atlas represent our best chance to maintain situational awareness during this crucial interval, though the capabilities of the existing Mars orbiters are limited in what they can detect even under optimal circumstances. The instruments on these spacecraft were designed for planetary science, not for the detection of exotic phenomena in passing interstellar objects. If there were true machines hidden among these cosmic travelers, their detection would require observational capabilities and analytical techniques that lie beyond the current frontiers of astronomical practice. The line between sufficiently advanced technology and natural phenomena may be finer than our current scientific paradigms can reliably distinguish. The question that emerges from this analysis is not whether we have found evidence of artificial visitors, but whether we would be capable of recognizing such evidence if it manifested in forms that lie beyond our present understanding of what technology should look like when projected across interstellar distances and millions of years of operation. If a machine were to masquerade as a comet, what, I wonder, would we actually see through our telescopes? Perhaps exactly what we are seeing now, objects that challenge our models while remaining just plausibly natural enough to fail the extraordinary evidence standards that extraordinary claims require. The universe keeps its secrets close, sharing them only with observers sophisticated enough to ask the right questions and patient enough to accept that some answers may lie beyond our current reach. Part 11. Shared Purpose. What common ground could they possibly have? On the grand cosmic stage, I find that coincidences are frequently read as conspiracies, and timing is interpreted as deliberate design when human minds attempt to find order in the cosmic chaos that envelops our small world. The arrival of two visitors within weeks of each other, displaying complementary characteristics and following trajectories that converge on our Sun in the same tight time frame, begins to feel less like a random event and more like the synchronized elements of a larger design. If one allows imagination to fill the voids where data is absent, one could entertain the notion that Swan R2 serves as a mobile logistics hub, while 3i Atlas operates as a high-speed reconnaissance craft. In this speculative scenario, the large comet with its vast tail is not a natural body of ice, but an intricate logistical platform, its apparent volatility masking the controlled management of resources and communication arrays. The smaller, more nimble 3i Atlas would function as a forward scout, gathering intelligence on the conditions of our solar system and transmitting it back to the main hub. This depot and scout configuration would explain several puzzling aspects of their observed behaviors. The precise trajectory and timing of 3i Atlas could be the result of deliberate navigation to pre-planned coordinates where Swan R2 would be positioned to receive data, offer supplies, or conduct repairs. The chemical signatures that we interpret as anomalous outgassing might, in reality, be controlled emissions, fuel transfers, atmospheric processing, or byproducts of technological systems operating under extreme thermal stress. Other interpretations suggest that both objects might be natural bodies that have been opportunistically co-opted by an ancient surveillance network distributed throughout our local galactic neighborhood. Rather than purpose-built spacecraft, they could be commandeered asteroids and comets, their surfaces or interiors modified to host automated systems that activate under specific conditions, such as the detection of electromagnetic signals from emerging technological civilizations. This piggybacking strategy would explain why both visitors exhibit characteristics that lie at the very edge of what is considered natural. Any civilization advanced enough to establish interstellar surveillance networks would likely prioritize stealth over overt presence, employing camouflage and mimicry to avoid provoking defensive responses from any species they encounter. Converting natural objects into technological platforms provides the perfect cover, allowing artificial systems to hide in plain sight among the countless rocks and ice bodies that populate interstellar space. The Sun itself might serve as more than just a gravitational anchor for these operations. Solar radiation provides an inexhaustible source of energy for systems designed to harvest electromagnetic waves, and the solar wind creates a dynamic plasma environment that could facilitate exotic physics beyond our current understanding. The ion winds streaming from our star could serve as both a communication medium and a power source for technologies that operate on principles we have yet to discover. Fantasies of surveillance grids envision networks of nodes strategically deployed throughout star systems, monitoring the evolution of planetary environments and the emergence of technological life. The Sun's gravity well creates natural collection points where data from remote sensors could be gathered, processed, and relayed to even more distant monitoring outposts. Our October 2025 convergence might simply be a routine data collection and transmission operation. The hunter and harvester dynamic presents a more ominous interpretation of the same temporal coincidence. If 3I Atlas is a predatory system designed to identify and neutralize potential threats, then Swan R2 might be a resource extraction platform designed to process whatever materials the hunter acquires. The size disparity between the agile scout and the massive processor would reflect their specialized roles in a larger enterprise that views our solar system as either an opportunity or a threat. The imagery that emerges from this speculative framework depicts scenes of the small courier moving inbound for its rendezvous, while the larger facility deploys collection arrays and processing machinery in anticipation of whatever materials or data the scout delivers. The apparent cometary activity we observe might be a cover for far more deliberate processes: energy harvesting, matter conversion, or the construction of temporary infrastructure to support extended operations in our vicinity. These scenarios are entirely constructs of the imagination, unsupported by any direct observational evidence, but they command human attention precisely because they provide a narrative structure for events that otherwise seem random and meaningless. The human mind resists coincidence, preferring explanations that imply intent and purpose, even when those explanations require extraordinary assumptions that go beyond the available data. The tension between coincidence and choreography touches upon deeper philosophical questions about the nature of intelligence in the universe and our ability to recognize it in unfamiliar forms. If advanced civilizations routinely operate with technologies that mimic natural processes, how would we ever distinguish between authentic natural events and highly sophisticated artificial systems? The clustering of events in October provides a concrete temporal framework around which these speculative narratives can be constructed. The September 12th perihelion of Swan R2, the October 3rd Mars flyby of 3I Atlas, the October 29th perihelion of 3I Atlas, and the October 21st closest approach of Swan R2 to Earth form a series of points in space and time that could represent either a cosmic accident or a carefully orchestrated design. Mythological precedents from human history offer archetypes for interpreting dual arrivals as signs or portents of profound change. Every culture on Earth has tales of celestial visitors that heralded the transition between historical epochs, lights in the sky that preceded the rise of empires, the fall of dynasties, or the emergence of new forms of knowledge and power. Perhaps 3I Atlas and Swan R2 are a modern iteration of these archetypal patterns. The recurring question that has served as a leitmotif throughout my investigation, is it a comet, a fortress, or the response to a message we didn't know we sent, acquires new depth when applied to a pair of visitors instead of a single anomaly. If one is the message and the other the reply, their rendezvous could signal the culmination of a conversation that began when our radio signals first started leaking into space decades ago. But it is at this point in our narrative that I must offer a word of guidance to the audience. We have now entered the realm of pure speculation, leaving the firm ground of observational evidence for the more perilous waters of imagination and possibility. The facts that underpin our inquiry, the October timeline, the chemical signatures, the orbital mechanics, all continue to point toward natural explanations, even as they tantalize us with more exotic theories. The question of a shared mission assumes coordination where none has been proven, purpose where coincidence is the more parsimonious explanation, and intelligence where natural processes provide adequate frameworks for understanding. These assumptions are as much a reflection of human psychological needs for meaning and pattern as they are of legitimate scientific puzzles about the behavior of interstellar visitors. Yet the possibility can never be entirely dismissed that some forms of advanced technology might be so sophisticated as to be indistinguishable from natural processes, either by design or as an unavoidable consequence of engineering that operates in harmony with, rather than in opposition to, the fundamental laws of physics. Such technology would require detection methods and analytical frameworks that lie beyond our current scientific capabilities. The ultimate test of these shared-purpose scenarios may arrive during the upcoming solar encounters, when both visitors will be subjected to their most intense heating and might reveal characteristics that were concealed during their cooler approach phases. If coordination exists between these objects, it might become manifest during the stress and opportunity of their perihelion passage, when their energy and communication requirements would be at their peak. The observational blackout imposed by solar glare during these critical phases means that the most definitive evidence for or against coordinated behavior might occur precisely when our instruments are blinded. We may emerge from the October silence with refined data on natural cometary processes, or we might find ourselves confronted with evidence that challenges our fundamental assumptions about what moves through the dark between the stars. If they do share a mission, what sort of mission would necessitate both a scalpel and a factory? The answer might be written in the fire of our sun during the hidden weeks ahead, when two cosmic visitors perform their final act in humanity's sight before vanishing into the archives of memory and speculation. Part 12. The Relay Hypothesis. A Cosmic Data Drop. In the domain of speculative astronomy, where I find imagination meets physics, few ideas capture the sense of cosmic purpose as effectively as the Relay Hypothesis. This is the concept that 3I Atlas functions as a data courier, while Swan R2 operates as a processing and transmission hub, with both converging on our Sun to complete an information exchange that has been in motion for years or even decades. I imagine 3I Atlas as the messenger, arriving from interstellar space carrying compressed archives of observations gathered during its long passage through our local galactic neighborhood. Its small size and nimble trajectory imply it is built for speed and maneuverability, not for bulk data storage. However, even a small object could contain vast quantities of information if encoded using highly advanced storage techniques. The anomalous chemical signatures we observe might not be natural outgassing, but a form of controlled data inscription, with information being physically etched into materials as the courier approaches its designated rendezvous. Swan R2, emerging from the outer reaches of our own solar system, fits the description of a data hub designed for processing and relay functions. Its immense size and spectacular tail could be a facade for sophisticated collection arrays and transmission systems engineered to operate in the extreme environment near stars. The apparent cometary activity could be a cloak for directed energy beams, plasma manipulation arrays, or exotic communication methods that work by modulating solar-wind interactions. The Sun itself is the crucial third element in this hypothetical relay system. Our star is the most potent energy source within hundreds of astronomical units, capable of powering systems that would be impossible to operate on portable power alone. But the Sun offers more than just raw energy. It provides a unique physical environment where gravitational lensing, magnetic field interactions, and plasma dynamics might enable communication technologies that operate on principles we do not yet comprehend. Gravitational lensing provides one potential mechanism for long-range communication using stellar-scale infrastructure. Einstein's theory of general relativity predicts that massive bodies like stars can bend and focus electromagnetic radiation, creating natural telescopes capable of detecting signals from immense distances. A sufficiently advanced civilization might position relay stations at the gravitational focal points of stars throughout the galaxy, using them as amplifiers for communication networks that span interstellar space. The plasma environment around our Sun offers another suite of possibilities for exotic physics applications. The solar wind carries charged particles throughout the solar system, creating electric currents and magnetic field structures that could potentially be manipulated by advanced technologies. I can envision systems that encode information directly onto plasma streams, embedding messages in the configurations of magnetic fields that stream past planets and out into interstellar space. Visualizations of this hypothetical data exchange depict scenes of industrial-scale processes masked by natural phenomena. Swan R2 unfurls collection surfaces that appear as clouds of dust and gas, harvesting solar radiation with an efficiency that makes photosynthesis seem primitive. Memory storage systems etch data into crystalline lattices capable of withstanding interstellar radiation and extreme temperatures. The fortress is bathed in ion fire as terabytes of compressed information flow between systems operating at the nexus of matter and energy. The concept of leveraging solar power for energy-intensive data operations reflects the enormous power requirements that any interstellar communication network would entail. Transmitting signals across galactic distances requires power outputs that represent a significant fraction of a star's total luminosity. The convergence in October of 2025 might be a strategic time window when solar activity, planetary alignments, and the positions of recipient stations create optimal conditions for highly efficient data transfer. The radio bubble emanating from Earth serves as the trigger for this entire hypothetical operation. Since the 1920s, our planet has been leaking electromagnetic radiation into space at an ever-increasing rate, creating an expanding sphere of artificial signals that now extends roughly 100 light-years in all directions. To any monitoring systems situated within this bubble, our radio leakage is unambiguous evidence of an emerging technological intelligence, a handshake signal that could activate dormant relay networks established long ago for this very eventuality. The temporal correlation between our technological development and the recent arrival of unusual interstellar objects takes on new meaning in this context. If automated surveillance systems detected our first radio broadcasts decades ago, they would have required time to dispatch courier systems from distant outposts, transit interstellar space, and coordinate with local relay infrastructure. The current wave of visitors may be the response phase of a communication protocol initiated by our own electromagnetic signals. Yet reality tempers these imaginative leaps with the persistence of observed data. We have detected none of the narrowband radio signals that any plausible interstellar communication system would likely produce. No anomalous accelerations have been observed that would indicate controlled propulsion or attitude control. The chemical signatures and physical behaviors of both objects remain within the spectrum of natural cometary phenomena, albeit at the more exotic end of that spectrum. NASA's official position continues to be that current evidence favors natural over artificial origins for both visitors. The agency's scientists emphasize that extraordinary claims demand extraordinary evidence, and despite their peculiar characteristics, neither 3I Atlas nor Swan R2 exhibits any features that definitively transcend what natural processes could produce under the right conditions. The question of, if true, who sent it, opens multiple speculative paths that tell us more about human psychology than about cosmic visitors. Perhaps they are missives from our own future, sent back through some manipulation of space-time that allows information to travel backward in time as well as forward in space. Perhaps they originate from parallel evolutionary lines that achieved interstellar capability millions of years ago and have been monitoring the development of intelligence throughout our local galactic neighborhood ever since. Alternative scenarios suggest both objects are components of an ancient automated network established by civilizations that achieved interstellar status long before Earth existed and have since vanished, leaving behind only their monitoring and communication infrastructure. In this view, we are not dealing with active intelligence, but with the technological ghosts of species that either transcended or went extinct eons ago, leaving automated systems that continue to execute their programming in the absence of their creators. A reality check for any interstellar relay hypothesis must account for the energy budgets and communication physics, which become implausible under quantitative examination. Broadcasting coherent signals over interstellar distances requires power outputs equivalent to a significant fraction of a star's total luminosity. Even receiving such signals would demand antenna arrays with effective apertures the size of planets. The infrastructure required for true interstellar communication networks lies beyond the industrial capacity of most conceivable civilizations. Yet these limitations are based on our current human understanding of physics and engineering. Civilizations that have mastered interstellar travel may operate on principles that render our concepts of energy and communication as obsolete as smoke signals are to users of fiber optic cables. What seems impossible with 20th century physics may be routine for species that have mastered 21st century physics. Just as our current capabilities would seem magical to observers from earlier technological eras, the relay hypothesis offers narrative satisfaction by transforming random cosmic encounters into purposeful intelligence gathering and communication events. It suggests that humanity has reached a threshold of technological development that makes us worthy of attention from intelligences that monitor the galaxy for emerging species. It implies that we are not alone and not unnoticed, that our progress is being monitored and perhaps even guided by forces operating on scales we can barely comprehend. But it also requires us to accept extraordinary claims based on evidence that remains stubbornly ordinary despite its unusual characteristics. The hypothesis assumes coordination where none has been proven, purpose where coincidence provides simpler explanations, and intelligence where natural processes offer sufficient theoretical frameworks for understanding what we see. The convergence in October of 2025 will serve as a critical test for any relay hypothesis. If a genuine data transfer occurs between our visitors, it should take place during their close approaches to the Sun, when energy is most plentiful and communication windows are ideal. The challenge will lie in distinguishing between natural cometary activity and the signatures of information processing systems operating under extreme thermal and radiation duress. What if the transaction is completed while our telescopes are blinded, hidden behind the glare of our own sun during the most critical phase of this hypothetical operation? We may emerge from the October silence with nothing more than refined measurements of ice sublimation and dust dynamics. Or we might find ourselves confronted with evidence that our solar system is a node in communication networks that span the galaxy. The relay hypothesis converts our Sun from a simple star into a cosmic post office, and our October visitors from random wanderers into mail carriers, completing routes that began in star systems whose names we do not know. Whether this conversion reflects a true discovery or simply the human need to find meaning in chaos remains the central mystery of our current cosmic moment. Part 13. The Harvest Scenario. Fuel fields and fires. The Sun burns with the cumulative force of 4.5 billion years of nuclear fusion, converting 4 million tons of matter into energy every second in a process so fundamental to our existence that we rarely consider its awesome power. But what if our star is more than just the anchor of our solar system? What if it is a cosmic refueling depot, a source of exotic fuels and forms of energy that civilizations harvest on timetables measured in millennia rather than human lifetimes? I can envision 3I Atlas and Swan R2 as components of an automated harvesting operation, arriving at our Sun not by chance, but according to cycles established long before human civilization emerged from the African plains. The smaller object functions as a surveyor and coordinator, assessing stellar output and plasma conditions to optimize collection efficiency. The larger facility deploys harvesting systems disguised as natural cometary phenomena, siphoning energy and matter from our star's outer atmosphere using technologies that blend engineering with physics. The harvest scenario forces us to reinterpret the spectacular cometary displays we observe as camouflaged industrial processes. The magnificent tail of Swan R2, stretching for degrees across the sky, could be masking engineered magnetic funnels designed to channel solar wind particles into processing units concealed within what appears to be a natural coma. The anti-solar alignment of ion tails, which we interpret as a passive response to charged particle pressure, could in fact be controlled exhaust streams from stellar farming engines operating on a scale that dwarfs any terrestrial industrial project. These hypothetical magnetic collection systems would need to operate with extraordinary subtlety to escape detection by our increasingly sensitive instruments. But advanced civilizations may have long ago mastered the art of working with natural forces rather than against them, creating technologies that amplify and channel natural processes rather than supplanting them with overtly artificial ones. What we perceive as standard comet behavior could in fact be the optimization of natural ion acceleration mechanisms for the purpose of resource extraction. The physics of such harvesting operations delves into realms where our current human understanding is limited. I consider the possibility of micro-wormhole networks temporarily stabilized by the extreme gravitational and magnetic fields present near the surfaces of stars. These microscopic space-time conduits could allow for the instantaneous transfer of harvested materials across interstellar distances, obviating the need for conventional propulsion to ferry resources back to distant consumer civilizations. The extreme fields required to sustain such wormhole networks would naturally exist only in environments like stellar coronas, where magnetic field strengths are thousands of times greater than Earth's surface magnetism, and gravity wells are deep enough for general relativity to become significant. Our Sun's October visitors might be positioning themselves to exploit these unique physical conditions during a brief window when field geometries are optimally aligned for exotic physics applications. Rhythmic pumping operations might be synchronized with cycles of solar rotation and magnetic field reversals, creating patterns of light and shadow that our instruments would interpret as natural brightness variations. The 27-day rotation period of the Sun imposes natural cadences on magnetic field orientation and plasma density, which sophisticated harvesting systems could exploit for maximum efficiency. October of 2025 might represent an optimal harvesting window, dictated by long-term cycles in solar activity and magnetic field topology. The isotopic composition of the solar wind presents another potential target for advanced harvesting operations. Our Sun produces helium-3 through its fusion processes, creating a light isotope that human fusion researchers consider the ideal fuel for advanced reactor designs. The natural solar wind carries this isotope throughout the solar system in concentrations far too diffuse for human exploitation, but highly advanced separation and concentration technologies could potentially extract useful quantities during close stellar passes. The motivations for resource extraction could extend beyond simple fuel harvesting to include exotic forms of matter and energy that are only available in stellar environments. The extreme temperatures and pressures in stellar chromospheres might permit the creation of exotic states of matter, quark-gluon plasmas, magnetic monopoles, or other theoretical particles that could serve as energy sources or manufacturing feedstock for civilizations operating on a galactic scale. Historical precedents from human resource extraction provide analogs for understanding how stellar harvesting might function. Our ancestors followed seasonal migration routes to exploit temporary concentrations of game animals, edible plants, and raw materials. Modern industrial civilization erects permanent infrastructure near coal seams, oil fields, and mineral deposits, which dictate the locations of cities and transport networks. Stellar harvesting is the logical extension of this pattern to cosmic scales and energy densities. The sound design implications of such operations stretch the human imagination. In the vacuum of space, no sound waves could propagate from these hypothetical harvesting systems. Yet their electromagnetic signatures might produce distinctive patterns that could be recognized by civilizations that know how to interpret them. Slow bass thrums in radio frequencies, distant crackles as magnetic field lines reconnect and release stored energy, all expressed as electromagnetic, not acoustic, phenomena. The station-keeping requirements for any real harvesting operation would necessitate continuous attitude control and position adjustments to counteract the complex gravitational and magnetic forces in stellar environments. These requirements would leave detectable signatures in the object's trajectories and rotational states, which our instruments should be able to detect if they exist. The absence of such signatures in our current observations argues against active harvesting scenarios. Yet we must acknowledge the limitations of our detection capabilities when confronted with technologies that may be thousands of years ahead of human understanding. Systems that maintain position and orientation by manipulating local magnetic fields might produce signatures so subtle that they fall below our current detection thresholds. What appears to be natural cometary behavior could, in fact, be the precise execution of complex industrial protocols. The ethical implications of stellar resource extraction raise profound questions about property rights and territorial claims on a cosmic scale. If advanced civilizations routinely harvest energy and matter from stars throughout the galaxy, is our sun considered a common resource? Or does our presence in orbit around it grant us some form of territorial sovereignty? Would harvesting operations necessarily view emerging civilizations like humanity as owners, competitors, or simply irrelevant biological phenomena? The distinction between actual comet behavior and imagined harvesting signatures is critical for evaluating these scenarios. Natural ion tails point away from the sun due to radiation pressure and charged particle interactions that obey well-understood physical principles. Any genuine harvesting operation would either have to operate within these constraints or produce detectable deviations from the expected tail geometry and plasma dynamics. Our current observations reveal ion tail behavior that aligns with theoretical predictions for natural interactions between a comet and the solar wind. There are no anomalous accelerations, no violations of expected tail orientations, and no evidence of controlled magnetic field manipulation beyond what natural plasma physics creates. The spectroscopic signatures we detect correspond to known molecular species undergoing familiar chemical processes under the influence of solar heating. If stellar harvesting operations were active in our solar system, we would expect to observe non-Keplerian orbital signatures as harvesting systems maintained optimal positions relative to changing solar conditions. The absence of such signatures in our tracking data for both 3I Atlas and Swan R2 indicates that whatever forces are governing their motion are gravitational, not artificial. But the harvest scenario retains its psychological appeal precisely because it transforms random cosmic encounters into elements of a vast industrial enterprise that spans both space and time. It suggests that our sun has purposes beyond simply providing energy for life on Earth, that our stellar system is part of economic networks that operate on scales we can barely imagine. The convergence in October of 2025 becomes a moment of cosmic commerce rather than mere gravitational mechanics, with both visitors playing specialized roles in resource extraction operations that follow timetables established long before human civilization began asking questions about the lights in the sky. If the sun is a station in some galactic resource network, how many routes dock here regularly, and what do they carry away into the cosmic night? The answer might be written in the fire and plasma of our star's corona, legible only to intelligences sophisticated enough to distinguish between the natural and the deliberately harvested in the dance of matter and energy that surrounds every star. Part 14. The conflict play: rescue, retrieval, or purge. In the unseen drama unfolding behind our sun's blinding glare, where my telescopes cannot penetrate and only imagination can set the stage, the events of October 2025 might constitute the final act of a cosmic struggle that has been building since two visitors first appeared in our skies. Three scenarios I consider in the realm of pure speculation, each casting our mysterious visitors in roles that transform them from passive wanderers into active participants in a larger contest for control, information, or cosmic security. The rescue scenario posits a narrative of technological salvation, with Swan R2 arriving not as an independent visitor, but as an emergency response to distress calls from 3I Atlas. In this interpretation, the interstellar visitor is not a healthy probe, but a damaged scout, its anomalous chemical signatures indicative of system malfunctions rather than an exotic composition. The nickel emissions without corresponding iron might signal hull breaches or component failures that are venting industrial materials into space as the craft struggles to maintain core functions. The dramatic appearance of Swan R2 from solar conjunction takes on new meaning as a rescue mission, its spectacular tail formation masking the rapid deployment of salvage equipment and stabilization systems. The massive comet's trajectory is timed to intercept 3I Atlas during the critical phase of its solar encounter, when thermal stress and radiation could deliver the final blow to any system still functioning on the crippled interstellar craft. The choreography of a rescue operation would require precise timing and coordination that could easily be mistaken for natural gravitational dynamics. Swan R2 would need to match the velocity and trajectory of 3I Atlas while deploying collection arrays disguised as cometary outgassing. The operation could involve transferring critical systems, retrieving data cores, or providing power and life support to crew members who have survived decades of interstellar transit only to face system failure during their final approach to our Sun. Alternative interpretations suggest a retrieval scenario where Swan R2 functions as a collector rather than a rescuer, arriving to gather intelligence or recover hardware from a probe that has completed its mission. 3I Atlas could be a reconnaissance platform designed to gather specific data about our solar system, with Swan R2 serving as the mobile storage and transport vehicle that will carry the collected information back to its point of origin. This retrieval could involve the physical engulfment of the smaller craft by the larger one, a process that might appear to our instruments as a collision or a fragmentation event. But rather than destruction, the apparent consumption would signify the successful recovery of intelligence assets after mission completion. The anomalous timing of both objects' solar approaches provides optimal conditions for data transfer and physical recovery while minimizing exposure to observation from Earth-based telescopes. The logistics of interstellar intelligence gathering might necessitate precisely this kind of staged operation, with specialized reconnaissance probes designed for single-use deployment. The immense energy costs of interstellar travel make it economically impractical to return small craft to their points of origin, but larger collector vessels could efficiently consolidate multiple completed missions while following trajectories that allow for an eventual return to base. The Purge scenario offers the darkest reading of the October convergence, with Swan R2 arriving not to assist 3I Atlas, but to sanitize the evidence of its passage through our solar system. In this context, the interstellar visitor is a beacon or communication platform that has exceeded its operational parameters, perhaps by transmitting information back to its controllers or by revealing too much of its artificial nature through detectable signatures. Swan R2 becomes the cleanup crew, tasked with erasing all evidence of technological visitation before emerging human intelligence can discover definitive proof of artificial origins. The purge would entail not just the destruction of 3I Atlas, but the dispersal of its wreckage in a way that makes forensic analysis impossible. Advanced disintegration technologies could reduce the probe to its constituent atoms, scattering them so widely that no trace of their artificial configuration remains. The timing of this hypothetical sanitization reflects a careful calculation of human observational capabilities and the impending observational blackout as both objects sink into the sun's glare. By scheduling the purge to occur when Earth-based telescopes are blinded, the cleanup crew ensures that no human instruments will witness the actual destruction and evidence disposal. Each scenario requires us to reimagine the spectacular cometary displays we observe as camouflaged operations involving technologies that operate at the intersection of physics and engineering principles we do not yet comprehend. The brilliant tails and expanding comas could be masking energy weapons, matter disintegrators, or exotic propulsion technologies that function by manipulating solar wind and magnetic field interactions. But these dramatic interpretations must contend with the persistent reality of observational data that shows no evidence of conflict, coordination, or artificial intervention. Both objects continue to follow trajectories dictated by gravitational mechanics, exhibiting spectroscopic signatures consistent with natural ice sublimation and dust emission. No anomalous accelerations suggest active maneuvering, and no electromagnetic signatures indicate artificial power systems or communication hardware. Mars is our only potential witness to whatever may transpire during the critical encounter phases, with orbiting spacecraft positioned to observe 3I Atlas during its October 3rd flyby. These robotic observers carry instruments designed for planetary science, not for detecting exotic phenomena, but they might capture evidence of any genuine interactions between our visitors that deviate from natural behavior. The European Space Agency's coordination of Mars-based observations represents our best chance to maintain surveillance during the periods when Earth-based telescopes are blinded by solar glare. However, the limitations of existing Mars orbiters mean that only the most dramatic deviations from expected natural behavior would be detectable at the distances involved. Communication delays between Earth and Mars further complicate real-time monitoring of any hypothetical conflict scenarios. The 12 to 24-minute signal travel time means that any intervention or response from Earth would be far too late to influence events unfolding on timescales of minutes or hours. We are relegated to the role of passive observers of whatever drama unfolds in the space between Mars and our Sun. The psychological appeal of conflict scenarios reflects human tendencies to interpret ambiguous events through familiar narrative templates involving struggle, resolution, and the triumph of one force over another. These dramatic frameworks offer emotional satisfaction by transforming cosmic coincidence into purposeful action, even when that purpose leads to destruction rather than creation. When the lights come back on and our telescopes can once again track both visitors, will we find the same number of objects that went behind our Sun? Will their orbits, compositions, and behaviors match predictions based on natural cometary models? Or will we be confronted with evidence that the universe contains conflicts and resolutions playing out on scales that dwarf human experience and challenge our understanding of what intelligence can achieve when it operates beyond the reach of our sight? Part 15. The October Silence. One by one, the instruments fall silent as both visitors sink into the Sun's overpowering radiance. Observatory feeds go dark, and coronagraphs are overwhelmed by light. The greatest show in our cosmic neighborhood vanishes behind a curtain of hydrogen fire, leaving us with only memory, speculation, and the steady ticking of atomic clocks measuring the time until the reveal. In government labs and university departments around the world, astronomers, including myself, collectively hold our breath. Social media buzzes with amateur theories and artistic impressions. The absence of new data becomes fertile ground for every possibility the human mind can imagine. In this imposed silence, every scenario feels equally plausible. Every interpretation carries the weight of potential truth. The spectrum of outcomes lies before us, like scenes from a film yet to be completed. One object re-emerging, its color or brightness transformed, permanently marked by its solar passage. The other appearing dimmer than expected, or maybe not at all, consumed by forces we cannot comprehend or measure. Coronagraphs might reveal a faint ring of dust where a single traveler once journeyed, a testament to some cosmic exchange conducted in private. Or perhaps nothing changes except our own yearning for significance, our deep hunger to find intent in the dance of gravitational forces and the beauty of sublimating ice. The true path of reality is paved with patient observation and careful measurement. The public viewing window for Swan R2 will peak in late September and October, offering amateur astronomers their prime chance to witness its magnificent tail sweeping across the twilight sky. 3I Atlas, if our models are accurate, is scheduled to re-emerge from behind the Sun in December, allowing professional instruments to resume their meticulous documentation of its chemical signatures and orbital dynamics. Current evidence points consistently toward natural explanations. Two remarkable comets whose temporal convergence is a product of orbital mechanics, not intelligent design. The real scientific value lies not in confirming our most fantastic theories, but in advancing our knowledge about the formation of other star systems, the chemistry of pristine materials from the farthest reaches of our galaxy, and the processes that transform objects when they confront the fierce radiation of our Sun. Yet, in the space between observation and interpretation, in the quiet between data points, narratives are born and flourish. We are pattern-seeking creatures in a universe vast enough to accommodate both mundane physics and extraordinary possibilities. The October silence becomes a screen onto which we project our most profound questions about intelligence, purpose, and our own place in the cosmic scheme. If an ancient machine did keep a rendezvous at our Sun, what would it find in our small corner of the cosmos? A young world inhabited by a curious species just starting to reach for the stars, already filling the electromagnetic spectrum with the clamor of civilization. Perhaps it would discover precisely what it was sent to find. Or perhaps it would find something unforeseen in the complex symphony of human hopes and fears, played out against the immense canvas of cosmic time. When the light of December brings our visitors back into focus, when the instruments resume their whispered transmissions of position, velocity, and spectral data, we will have our answer to the question that has resonated through 14 chapters of awe and speculation: comet, fortress, or reply. Until then, we wait in the October silence, held in the gravitational arms of our Sun, wondering what stories the darkness might be writing in languages we have not yet learned to decipher. The universe guards its secrets jealously, but it rewards our patience with revelation. What I found especially captivating was the chance that dust from the belt might engage with Atlas's distinct chemistry in unforeseen manners. The majority of research on dust impacts presumes compositions dominated by water ice, which is characteristic of comets in our solar system. However, carbon dioxide acts differently when heated by an impact, subliming at cooler temperatures and potentially leading to more volatile reactions to outside forces. The bands of dust and the zodiacal cloud that pervade the inner solar system could introduce further complexities. These features, which arise from dust spiraling inward after asteroid collisions, establish a baseline environment of particle strikes that changes with both position and time. As Atlas traverses regions with varying dust densities, its luminosity and the shape of its tail could shift in ways that provide insights into both the comet's characteristics and the previously unmapped dust conditions. A beneficial outcome of possible dust collisions is their scientific importance. Even destructive events would broaden our collection of interstellar matter, scattering previously concealed interior compositions across the coma, where our telescopes could conduct spectroscopic analysis. In a way, the dust of the asteroid belt could function as a natural probe, extracting samples from Atlas's core and making them accessible for remote study. The timing of these potential encounters is paramount. Each week that Atlas remains whole, enhances the scientific yield of the mission, permitting more advanced measurements and extended observation of compositional shifts. Yet each week also means a deeper journey into the belt's most congested areas, elevating the likelihood of collisions with bigger particles that might provoke more drastic responses. Perhaps most significantly, the environment of dust and minor collisions poses a challenge that no previous interstellar guest has encountered. Neither Oumuamua nor Borisov formed substantial comae while navigating through dense particle fields. Atlas is breaking new ground, in both a literal and figurative sense, as the premier active interstellar comet to travel through the perilous dust storms of the asteroid belt. The result would hinge on elements we were just starting to grasp: the delicate equilibrium between Atlas's structural integrity and the mounting pressures of its journey through the belt, the interplay of its unique chemistry with the dust impact environment, and the internal compositional gradients that dictate how the object reacts to external stimuli. Every single observation was now vital, with each measurement of brightness possibly being the final unobstructed view of an intact interstellar nucleus. The concealed threats of dust and minor collisions were not as spectacular as catastrophic asteroid strikes, but they could be equally crucial in deciding whether Atlas would endure to unveil its secrets or slowly break apart under the cumulative strain of traversing our cosmic vicinity. The ancient traveler was being put to a test unlike any it had faced during its billion-year voyage through interstellar space, and the conclusion was still very much in doubt. Part 10. Controlled or Autonomous. In July of 2025, while global attention was fixed on the recently found interstellar guest, a group of scientists released a speculative article that would capture imaginations and make headlines across the planet. The archive preprint, written by Abraham Loeb and his associates, offered what they termed a pedagogical thought experiment. It raised the prospect that 3I Atlas might not be a natural comet, but instead an artificially made object, perhaps even with hostile intentions. This idea was not entirely without precedent. Loeb had earlier suggested that Oumuamua could be alien technology, citing its strange acceleration and absence of visible outgassing as possible proof of artificial origin. Atlas, however, posed a different kind of mystery. It was clearly active, forming the coma and tail anticipated from natural comets. Still, its path and timing appeared almost too perfect for thorough investigation. The paper's wording was meticulously framed with scientific prudence, proposing the alien hypothesis as one of many possibilities rather than a firm conclusion. Yet, in the media landscape of 2025, subtle academic speculation swiftly became sensational news. Tabloid articles and opinion columns exaggerated the language far beyond what the original authors had suggested, creating a cycle of increasingly sensational assertions. The mainstream scientific community responded quickly and with composure. NASA persisted in classifying Atlas as a natural comet, referencing initial spectroscopic findings that revealed typical cometary volatiles, although in unusual proportions. The James Webb Space Telescope's discovery of carbon dioxide and water vapor aligned with the expectations for natural sublimation, even though the specific chemical makeup was different from that of typical solar system objects. Crucially, none of the observational indicators that would point to artificial construction had been found. Investigations for radio signals at frequencies typically used for communication detected only natural thermal emissions. The object's light curve displayed fluctuations consistent with an irregularly shaped rotating nucleus, not the steady brightness one would expect from a manufactured sphere or cylinder. There was no sign of controlled acceleration beyond what could be attributed to normal outgassing. The timing arguments that stirred public interest were less convincing upon detailed examination. While Atlas's near-ecliptic path did guide it through the most scientifically compelling areas of our solar system, the principles of orbital mechanics dictate that any object arriving from interstellar space has a limited set of possible routes. The seeming coincidence of ideal positioning might just be because we are most likely to find and examine objects that travel through regions where our telescopes can effectively see them. The Mars encounter distance of 0.19 astronomical units, often highlighted as suspiciously convenient for observation, actually signifies a fairly common close pass for objects on hyperbolic trajectories. Random orbital mechanics regularly produces such encounters, and the presence of our spacecraft at Mars to capitalize on the opportunity is a result of human foresight, not alien design. SETI researchers, while keeping a healthy dose of skepticism about the alien theory, viewed the speculation as a chance to carry out passive monitoring efforts during crucial stages of Atlas's voyage. Radio telescopes across the globe set up opportunistic observations for the Mars flyby and solar approach, listening for any signals that could suggest an artificial source. The lack of any detected transmissions, while not disproving technological construction, did not provide any evidence to support the hypothesis. The search for mini-probes or deployed objects, as suggested in some media reports, yielded no observational backing. High-resolution imaging efforts found no separate objects accompanying Atlas, no indication of material being intentionally released, and no organized patterns in the coma or tail that might suggest technological elements. Perhaps most tellingly, the chemical signatures identified through spectroscopic analysis were consistent with what is expected for natural materials formed under alien stellar conditions. The composition, rich in carbon dioxide, while uncommon for solar system comets, aligned with models of objects formed in the outer parts of protoplanetary disks around other kinds of stars. The isotope ratios, where they could be measured, showed values in line with natural nucleosynthesis processes, not the artificial isotopic signatures that might come from technological manufacturing. The speculation did, however, bring to light important questions about how the scientific community should handle genuinely unusual observations. The distinct properties of both Oumuamua and Atlas showed that interstellar visitors could behave in ways beyond our local experience, making it vital to differentiate between naturally exotic events and potentially artificial signs. Media literacy emerged as a key element in the public's grasp of the speculation. The shift from a tentative academic hypothesis to sensational headlines demonstrated how scientific uncertainty can be magnified and warped in public conversations. The original researchers' careful qualifications and focus on the pedagogical aspect were often lost in reports that portrayed the alien hypothesis as a serious scientific assertion rather than a thought experiment. Cultural influences also affected how the speculation was received. The earlier discussions about Oumuamua had prepared the public to see interstellar visitors as potentially enigmatic or artificial. Science fiction stories about alien probes and first contact events offered ready-made ways to interpret strange astronomical findings. The genuine scientific enthusiasm about Atlas's unique characteristics could easily be twisted into evidence for more exotic theories. The ethical ramifications of such speculation merited careful thought. If real evidence of artificial construction were ever found, issues of disclosure, international cooperation, and public communication would become paramount. The Atlas speculation served as a valuable trial run for how the scientific community might address truly anomalous discoveries in the future. But for the object speeding through the asteroid belt in late 2025, the alien hypothesis was not backed by observational evidence. The unusual chemistry that made Atlas so scientifically captivating was better explained by natural processes at work under foreign stellar conditions than by technological fabrication. The trajectory that brought it through our most observable zones was a product of the mathematics of orbital mechanics, not intelligent guidance. The speculation had fulfilled its role as a thought experiment, sparking public interest and emphasizing the extraordinary nature of interstellar visitors. But as Atlas continued its journey toward its solar encounter, the evidence overwhelmingly indicated a natural origin. It was an ancient comet formed around another star, carrying samples of alien chemistry that were valuable precisely because they were natural outcomes of cosmic evolution. The real puzzle was not whether Atlas was artificial, but how natural processes in other stellar systems could create objects so different from what we know locally. That mystery was worthy of the same focused pursuit once given to speculation about alien construction, and the discoveries would be just as compelling as any science fiction plot. As Atlas neared its closest approach to the Sun, the question was not whether it was controlled or autonomous. It was whether this natural wonder would last long enough to reveal all the secrets of its alien chemistry and ancient past. Part 11. If destroyed, a shattered visitor. The scenario develops slowly, almost unnoticeably at first, as thermal pressures and internal forces accumulate within Atlas's ancient core. What starts as minor fluctuations in brightness and asymmetrical jets transforms into something more spectacular, the slow-motion breakup of an interstellar visitor that has endured for billions of years, only to be overcome by the harsh conditions of our inner solar system. The physics behind cometary fragmentation is both powerful and strangely elegant. As the Sun's heat reaches deeper into the nucleus, volatile substances trapped inside the ice-rock mixture start to sublimate quickly, generating internal pressure that looks for the easiest escape route. Fissures that developed over eons of thermal cycling in interstellar space turn into the centers for explosive outgassing events that can literally tear the nucleus to pieces. The visual changes would be clear to seasoned comet watchers. First, the central condensation, the luminous core that is the reflected sunlight from the solid nucleus, starts to stretch out and form several bright points. High-resolution images would show that what was once a single body is now becoming several, each following slightly different paths as they drift apart due to rotational forces and uneven outgassing within days or weeks of the initial split. The brightness behavior alters dramatically. Instead of the gradual increase anticipated from normal solar heating, Atlas displays a rapid brightening followed by an equally swift dimming as each piece uses up its surface volatiles and then goes dormant. The overall coma widens and becomes more spread out, losing the distinct central point that signifies an intact nucleus. The tail structure reacts instantly to the fragmentation, splitting into multiple parts as different pieces contribute their own streams of gas and dust. What was once a single unified plasma tail becomes a complex interwoven structure reflecting the multiple ion sources now scattered along the comet's path. The dust tail, no longer supplied by a single source, fans out into a broad sheet that can stretch across large areas of the sky. For observers on Earth, a fragmenting atlas would present both stunning viewing chances and deep scientific disappointment. The larger surface area from multiple fragments often causes a boost in brightness that can make comets visible to the naked eye, even from great distances. But the very fragmentation that produces this temporary show also annihilates the pristine interior materials that are our only samples of interstellar chemistry. The question of a meteor shower always comes up when a comet fragments, but Atlas's trajectory offers comforting answers. The pieces would keep moving on the same hyperbolic path as the original object, speeding away from the Sun on routes that never cross Earth's orbit. Unlike periodic comets that can leave debris trails in Earth-crossing orbits, interstellar visitors take their fragments completely out of our vicinity. The dust and gas freed by fragmentation could have more subtle consequences. An enhanced zodiacal light, the dim glow from sunlight bouncing off interplanetary dust, might show temporary bright spots in areas where Atlas debris is concentrated. Radio observations might pick up brief increases in plasma wave activity as the expanded ion cloud interacts more strongly with the solar wind. But these effects would be localized and fleeting, presenting no danger to Earth or its technology. From a planetary dynamics standpoint, the fragmentation of Atlas would be virtually insignificant. The total mass involved, likely less than a few trillion tons, is a trivial disturbance compared to the gravitational forces that shape planetary orbits. Even if all the fragments were somehow gathered in one spot, the gravitational effects would be too slight to detect with our most precise instruments. The scientific worth of fragmentation is a complex balancing act. On one side, a breakup ruins the structural integrity that holds the layered composition and formation history within the nucleus. The gradual mixing and spreading of internal materials make it impossible to know their original arrangement or the sequence of accretion that formed the comet around another star. On the other side, fragmentation exposes interior materials that would otherwise be concealed beneath radiation-damaged surface layers. Freshly broken surfaces reveal previously hidden ices for spectroscopic study, potentially unveiling chemical signatures that were not visible when contained within the whole nucleus. The expanding cloud of debris offers a larger area for telescopic observation, making it easier to find trace elements and isotope ratios. Comparative studies with comets, ISON and C2019Y4 Atlas offer a basis for understanding how fragmentation occurs and what observational signs to anticipate. Both objects displayed similar trends, an initial brightening as surface area grew, followed by a swift dimming as small pieces depleted their volatile reserves. The debris clouds dispersed over months to years, eventually becoming untraceable as they spread out along their extended orbital paths. High-resolution imaging would be essential for documenting the fragmentation and figuring out if it is caused by internal stress, external impacts, or a mix of both. The Hubble Space Telescope's past observations of fragmenting comets have offered detailed looks at nucleus breakup, showing how individual parts separate and change independently over time. The European Space Agency's future Comet Interceptor mission, scheduled for launch in the late 2020s, was initially planned to study pristine comet nuclei up close. If Atlas were to break apart, the scattered debris might actually offer multiple targets for such missions, each showing different facets of the original object's composition and structure. Perhaps most movingly, the fragmentation of Atlas would mark the end of a saga that started when our galaxy was younger and quite different from what it is today. An object that had roamed between the stars for billions of years, withstanding cosmic ray bombardment, gravitational pulls, and the severe environment of interstellar space, would fall not to some grand cosmic disaster, but to the gentle heat of our familiar sun. The emotional impact of such an event should not be dismissed. Comets have always symbolized impermanence in human culture, beautiful visitors that show up briefly before disappearing forever. An interstellar comet elevates this symbolism to cosmic proportions, representing the immense spans of time and distance that separate us from other stellar systems. Its destruction would be a reminder that even journeys lasting billions of years can end in what is a geological instant. Yet, even in its destruction, Atlas would continue to contribute to science. The scattering fragments would carry isotope signatures and chemical traces into the outer solar system, where future missions might find and analyze them decades or centuries from now. The observational data from the fragmentation would help refine models of comet structure and composition, improving our understanding of similar objects for generations to come. The likelihood of destruction was genuine, backed by historical examples and the growing signs of internal stress shown by Atlas's unpredictable brightness. But destruction would not signify failure. It would simply be a different kind of scientific discovery, one that exchanged long-term preservation for immediate access to materials that had been hidden since our galaxy's early days. As Atlas sped toward its October solar encounter, the fragmentation scenario was just one of several possible futures. The ancient traveler might still be strong enough to withstand the thermal stress and reappear whole on the other side of perihelion. But if it did not, if the pressures of the solar encounter were too great for billion-year-old ice and rock, then we would see the spectacular conclusion of an interstellar journey that began when the universe itself was barely half its current age. In any case, Atlas would teach us something profound about the nature of materials formed around other stars, the physics of objects that connect stellar systems, and our own position in a galaxy filled with wandering worlds we are only just beginning to find. Part 12. If redirected, a new orbit. The notion has sparked imaginations ever since the first interstellar visitor was found. Could a chance gravitational pull divert Atlas from its hyperbolic path, trapping it for good within our solar system? This scenario speaks to our deepest wishes for cosmic companionship, the idea that this ancient wanderer might forsake its billion-year voyage to become a permanent resident among our familiar planets. The mathematics, however, paints an entirely different picture. Atlas possesses a hyperbolic excess velocity of about 58 kilometers per second, which is a kinetic energy far greater than any encounter in our solar system could overcome. To grasp the magnitude, one must realize that even Jupiter, our most massive planet by a wide margin, can only change an object's velocity by approximately 2 kilometers per second during a close pass. Compared to Atlas's immense hyperbolic energy, such disturbances are minor adjustments rather than significant redirections. Gravitational capture necessitates what orbital mechanics experts call a deep encounter, a close approach that lets a massive body bend the incoming trajectory through wide angles while also dissipating excess energy through tidal forces or other mechanisms. For Atlas, even the nearest planetary pass happens at Mars, where the flyby distance of 0.19 astronomical units is considered a distant encounter for capture purposes. The energy levels involved make permanent capture through gravitational forces alone virtually impossible. Atlas would have to shed more than 99% of its kinetic energy to switch from a hyperbolic orbit to an elliptical one tied to the Sun. No sequence of planetary encounters in our solar system could accomplish such a drastic energy reduction, especially with the object's retrograde trajectory that reduces rather than enhances gravitational assists. But small redirections are certainly possible and could be observable. Mars could slightly alter Atlas's trajectory, changing the exact timing of its solar approach or minorly adjusting its departure angle. Venus, at 0.65 astronomical units in November, might add further small perturbations. The combined effect of these encounters could shift Atlas's final exit path by detectable amounts without fundamentally altering its hyperbolic character. More interestingly, non-gravitational forces could influence the trajectory. The uneven outgassing that produces comet tails also creates small but continuous accelerations that can add up over time. If Atlas develops strong, directionally focused jets during its solar approach, these forces could act like minuscule rocket engines, nudging the trajectory in ways that add to gravitational disturbances. The Rosetta mission showed how outgassing forces can significantly change comet orbits over many perihelion passages. For 67P Churyumov-Gerasimenko, uneven jets altered the orbital period by several minutes per orbit, small changes that accumulate into major shifts over thousands of years. Atlas, with its distinct carbon dioxide-rich chemistry, might show outgassing patterns different from typical water-heavy comets. Nevertheless, even dramatic non-gravitational accelerations could not overcome Atlas's fundamental hyperbolic nature. The object has too much energy to be captured. No matter how its path might be altered by outgassing, any redirection would simply change the direction it leaves our solar system, not prevent its departure altogether. The idea of it hiding in the belt is another fascinating but ultimately unfeasible scenario. Some speculative ideas have proposed that Atlas might somehow get trapped among the objects in the asteroid belt, blending in as a local resident while secretly retaining its interstellar origins. Orbital mechanics makes this fantasy impossible. Hyperbolic trajectories do not allow for closed orbits around the Sun, regardless of where they might travel through the solar system. Observations after perihelion will be vital for recording any trajectory changes that do happen. Atlas is set to emerge from solar conjunction in early December 2025, giving us chances to measure any shifts in its orbit from its solar encounter and planetary interactions. These measurements will help refine models of non-gravitational forces and improve predictions for future interstellar visitors. The observation opportunities go far beyond simple trajectory tracking. Multiple spacecraft throughout the inner solar system might get a look at Atlas during various stages of its journey, providing parallax measurements that enhance orbital calculations and detect subtle perturbations. The Mars encounter on October 3rd is a particularly valuable chance for spacecraft orbiting the red planet. NASA's Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express, along with assets on the surface like the Perseverance rover, all have instruments that can detect bright comets in favorable conditions. While organizing such observations is complicated, the potential scientific reward could warrant the effort needed to arrange special viewings. The trajectory changes, no matter how small, have implications for larger questions about interstellar object populations and their interactions with planetary systems. Understanding how solar system encounters affect the paths of visiting objects helps astronomers model the long-term evolution of interstellar populations and predict detection rates for upcoming surveys. Perhaps most importantly, careful trajectory monitoring serves as a test of our understanding of non-gravitational forces and plasma interactions. If Atlas's departure path deviates from gravitational predictions by measurable amounts, those deviations can be linked to outgassing forces, radiation pressure, or electromagnetic interactions with the solar wind. Each measurement refines our knowledge of how interstellar materials react to stellar environments. The ultimate outcome is clear. Atlas will leave our solar system on a modified but still hyperbolic trajectory, taking its samples of alien chemistry back into interstellar space. The exact direction of its departure and the precise timing of its exit might be changed by its solar encounter, but the fundamental result, a return to the galactic wilderness, cannot be altered by any realistic combination of gravitational and non-gravitational forces. This certainty is both disappointing and relieving. The disappointment stems from our inability to keep this extraordinary visitor for prolonged study. The relief comes from knowing that Atlas will continue its cosmic voyage, possibly carrying samples of our solar system's environment to other stellar vicinities billions of years from now. In a way, Atlas is a cosmic envoy, sampling conditions around different stars and distributing materials between stellar systems on timescales comparable to galactic evolution. Its brief stop in our neighborhood is just one chapter in a story that spans the history of the galaxy, connecting stellar systems across space and time in ways that are beyond human comprehension. The redirection scenarios, however enticing to our imagination, cannot overcome the fundamental physics of interstellar trajectories. Atlas will stay a visitor, not a permanent occupant, leaving our solar system with slightly changed momentum, but with its mystery fully intact. The brief encounter will provide us with data, memories, and questions that will endure long after our own civilization can recall this ancient wanderer from the stars. Part 13. The alien hypothesis expanded. The speculation that started with a single arch of preprint in July of 2025 had grown into something far more intricate and debated by the time Atlas was crossing the asteroid belt. What began as an academic thought experiment, could this interstellar visitor be alien technology, had been transformed through media amplification and public imagination into assertions that seemed to have a life of their own. Abraham Loeb and his co-authors had deliberately presented their original paper as pedagogical, using terms like possibly hostile not as firm statements, but as extreme examples to show that extraordinary evidence is needed to back extraordinary hypotheses. The scientific method requires that all possibilities, even improbable ones, be considered, as long as they lead to testable predictions that can differentiate between various explanations. But the path from scientific speculation to public narrative showed how extraordinary claims can get ahead of the evidence that supports them. Social media algorithms, built to foster engagement over accuracy, amplified the most sensational views while often leaving out the careful qualifications and statements of uncertainty that were part of the original research. The scientific community's reaction remained composed and based on evidence. NASA's official stance labeled Atlas a natural comet, citing multiple sources of observational proof. The spectroscopic signatures found by the James Webb Space Telescope and ground-based observatories were in line with what is expected from natural sublimation, even if the particular chemistry was different from typical solar system objects. More importantly, none of the definitive signs that would point to artificial construction had been found, despite close monitoring by multiple facilities. Radio searches revealed no coherent signals at frequencies often used for communication or navigation. Optical monitoring showed no signs of controlled acceleration beyond what could be attributed to normal outgassing. High-resolution imaging did not reveal any geometric structures or surface features inconsistent with natural formation. The burden of proof for extraordinary claims demands extraordinary evidence, and such evidence simply had not appeared, despite months of thorough observation. The alien hypothesis was still possible in the abstract sense that most unfalsifiable ideas are possible, but it did not have the observational backing to elevate it from speculation to serious scientific consideration. SETI researchers, while maintaining proper scientific skepticism, had taken the chance to conduct passive monitoring campaigns during key moments of Atlas's journey. The Breakthrough Listen project and other radio survey programs allocated dedicated observation time around crucial dates, the Mars encounter, solar approach, and departure phases, when any supposed technology might be most likely to activate or transmit. The lack of any detectable signals, while not completely disproving a technological origin, failed to provide the positive evidence needed to support such claims. In science, negative results are meaningful. They narrow down the range of possible explanations and rule out hypotheses that make specific, testable predictions. The search for deployed objects or mini-probes had also produced negative results. Numerous high-resolution imaging efforts, including observations by the Hubble Space Telescope and ground-based adaptive optic systems, found no separate objects traveling with Atlas, no signs of structured material being released, and no geometric patterns in the coma or tail that might suggest technological components. Perhaps most tellingly, the isotopic signatures identified through detailed spectroscopic analysis were consistent with what is expected for natural materials formed through stellar nucleosynthesis. The carbon, oxygen, and hydrogen isotope ratios, where they could be measured, were within the ranges predicted for objects formed in different galactic environments, rather than showing the artificial signatures that might come from technological construction or propulsion systems. The cultural context of these speculations deserves its own analysis. The earlier debates about Oumuamua had positioned interstellar visitors as potentially mysterious objects, deserving of exotic explanations. Science fiction narratives about alien probes, first contact events, and hidden technological surveillance offered ready-made interpretive frameworks that could be applied to any unusual astronomical discovery. Media coverage often highlighted the most sensational possibilities while downplaying the careful uncertainty quantification that characterizes responsible scientific communication. Headlines that declared, "Scientists say comet could be alien probe," rarely conveyed the conditional language, probability assessments, and alternative explanations that were in the original research papers. The situation brought to light important questions about science communication in an age of rapid information spread and algorithmic amplification. How should researchers balance legitimate scientific speculation with public understanding? What responsibilities do scientists have when their hypotheses are misrepresented or sensationalized in popular media? Educational opportunities arose from the controversy. The alien speculation provided teachable moments about the scientific method, the nature of evidence, and the process by which extraordinary claims are assessed within the scientific community. The progression from hypothesis to testing to conclusion offered clear examples of how science distinguishes between speculation and established knowledge. The ethical implications of such speculation also deserved consideration. If genuine evidence for artificial construction were ever found, issues of disclosure, international coordination, and public communication would become paramount. The Atlas controversy served as a useful case study for how the scientific community might handle truly anomalous discoveries in future encounters. But perhaps most importantly, the alien speculation had served to highlight just how remarkable Atlas was as a natural object. The unusual chemistry, the convenient trajectory, the timing of discovery, all the factors that made a technological origin seem plausible were actually evidence for the incredible diversity of natural processes operating throughout our galaxy. The carbon dioxide-rich composition revealed formation conditions unlike anything in our local stellar neighborhood. The near-ecliptic trajectory demonstrated that interstellar space contains objects following every conceivable orbital geometry. The detection timing reflected our improving ability to discover and characterize objects that would have remained invisible to previous generations of telescopes. In a very real sense, Atlas was far more interesting as a natural phenomenon than it would have been as alien technology. Technological objects, however advanced, operate within constraints imposed by physics, engineering, and presumed rational purposes. Natural objects, shaped by processes we don't fully understand, operating under conditions we can barely imagine, can exhibit behaviors that transcend our current theoretical frameworks. The real mystery wasn't whether Atlas was controlled by alien intelligence, but how natural processes in foreign stellar environments could produce objects so different from our local experience. That mystery was worth pursuing with the same intensity once directed towards speculation about technological construction, and the answers would prove just as profound as any first contact scenario. As Atlas continued its journey through the asteroid belt, the evidence pointed overwhelmingly toward a natural origin. Not because aliens were impossible, but because the natural universe was strange enough to explain everything we were observing. The cosmos didn't need artificial enhancement to generate objects that challenged our understanding and fired our imagination. The alien hypothesis had done its job, encouraging rigorous observation and analysis while generating public interest in interstellar visitors. But the natural explanation emerging from that analysis was proving far more fascinating than any science fiction alternative. Atlas was teaching us that reality, when viewed on cosmic scales, could be more exotic than our wildest speculations about alien technology. Part 14. The Wake-Up Call. The discovery of Atlas was more than just another astronomical finding. It was a glimpse into our future, a preview of a time when interstellar visitors might become common rather than exceptional. Our current sky surveys, though impressive to us now, detect only a small portion of the objects passing through our cosmic vicinity at any moment. The catalogs kept by NASA, ESA, and ground-based survey programs list millions of known objects, from near-Earth asteroids to distant Kuiper Belt inhabitants. But these databases, however extensive they seem, mainly document objects that are part of our solar system, permanent residents held by the Sun's gravity, and following predictable orbits that can be projected centuries ahead. Interstellar visitors pose entirely different problems. They show up unannounced from random directions, travel on hyperbolic paths that take them quickly through our detection range, and often stay visible for only weeks or months before they are too faint for our instruments to see. The finding of Atlas, like that of its predecessors, Oumuamua and Borisov, was as much a matter of luck and timing as it was a result of systematic search efforts. This is set to change profoundly with the completion of the Vera C. Rubin Observatory, previously known as the Large Synoptic Survey Telescope. Starting its work in the mid-2020s, this groundbreaking facility will carry out a decade-long survey of the southern sky, capturing images of the entire visible universe every few nights with remarkable depth and accuracy. Current predictions for the rate of interstellar object detection differ significantly, depending on assumptions about size distributions, approach angles, and instrumental sensitivity. Conservative estimates suggest the Rubin Observatory could find 1 to 2 interstellar visitors each year, a tenfold increase over present discovery rates. More hopeful scenarios, based on theoretical models of galactic object populations, foresee dozens of detections annually once the survey is fully operational. The consequences of such discovery rates go far beyond simple object catalogs. Each interstellar visitor brings distinct chemical signatures and formation histories from different stellar environments. Systematic studies of numerous objects would uncover patterns and connections that are impossible to see from isolated cases like Atlas. Statistical analysis of interstellar populations could help refine models of planetary formation, stellar evolution, and galactic chemical development. But higher discovery rates also bring new difficulties for rapid observation and characterization. Atlas had the advantage of months of early warning and coordinated observation campaigns involving multiple facilities around the world. If interstellar visitors become common enough, the astronomical community will require automated detection algorithms, prearranged response plans, and adaptable scheduling systems that can react to unexpected findings. The Atlas experience has taught us valuable lessons for handling future interstellar encounters. The collaboration between NASA, ESA, NOIR and international partners showed how effectively the global astronomical community can rally resources for rare opportunities. The swift use of space-based assets like the James Webb Space Telescope and Hubble highlighted the importance of flexible scheduling and the ability to override priorities. Perhaps most crucially, Atlas has acted as a practice run for public communication and media relations during high-profile astronomical events. The progression from technical discovery announcements to broad public interest to sensationalized speculation demonstrated both the opportunities and the challenges of conveying cutting-edge science to a general audience. The planetary defense aspect introduces another layer of intricacy to the detection and characterization of interstellar objects. While Atlas presented no danger to Earth, future visitors might travel on paths that bring them closer to our planet or its orbit. Differentiating between harmless interstellar visitors and potentially dangerous objects demands quick orbit determination and precise size assessment, skills that current survey systems are still honing. The technical framework for managing increased detection rates is slowly being established. Machine learning algorithms can now spot moving objects in survey data with an accuracy that rivals human analysts. Automated follow-up systems can initiate spectroscopic observations at various facilities based on set criteria. Communication networks can distribute discovery details to the global astronomical community within hours of detection. Educational chances increase as interstellar visitors become more frequent. Each new discovery offers fresh material for discussing stellar formation, planetary dynamics, and the chemical evolution of galaxies. The variety of objects, some like familiar solar system bodies, others with completely alien traits, provides natural laboratories for comparative planetology on an interstellar scale. The challenges of data archival and analysis are just as substantial. Each well-observed interstellar visitor produces terabytes of imaging, spectroscopic, and photometric data that must be processed, stored, and made accessible for future research. The ATLAS data set, gathered over months of intensive observation, will be a benchmark for comparing future discoveries and testing theoretical models. International cooperation becomes even more vital as detection rates rise. No single nation or observatory system can fully characterize multiple interstellar visitors at once. Sharing telescope time, coordinating observations, and combining analytical skills require agreements and protocols that go beyond traditional institutional lines. The technological implications reach beyond astronomy to spacecraft design and mission planning. If interstellar visitors are common enough, dedicated interceptor missions become practical. Spacecraft positioned at key locations within the solar system prepared for quick launch to meet newly discovered objects. Conceptual plans for such missions are already in the literature, waiting for detection rates high enough to warrant their development. Amateur astronomers will take on increasingly significant roles in detecting and monitoring interstellar visitors. Modern CCD cameras and computerized telescopes have democratized astronomical observation to a degree that was unimaginable just decades ago. Networks of amateur observers can offer continuous monitoring that professional facilities, with their competing demands and limited telescope time, cannot provide. The wake-up call from ATLAS is not just about technical readiness, but also about philosophical preparedness. As interstellar visitors become routine, the human perspective on our place in the galaxy will undoubtedly change. We are not solitary inhabitants of a unique stellar system, but participants in a vast galactic ecosystem where materials and possibly life itself move between stars over millions and billions of years. Each interstellar visitor is a cosmic messenger, carrying samples of chemistry and physics from stellar environments we may never see directly. The accumulated data from dozens or hundreds of such objects will offer insights into galactic evolution, planetary formation processes, and the distribution of organic materials throughout our local region of the Milky Way. This preparedness is not just about defense or scientific opportunity, it is about acknowledging our membership in a much larger cosmic community. The materials in our own bodies, forged in the cores of stars and scattered by supernovae, share common origins with the substances traveling between stars on objects like ATLAS. We are not studying alien chemistry, but distant relatives in the vast family of cosmic materials. As ATLAS continues its journey toward its solar encounter, it carries with it the hopes and preparations of an astronomical community learning to expect the unexpected. The ancient wanderer has already taught us that our cosmic neighborhood is far more dynamic and interconnected than previous generations ever imagined. The visitors yet to come will complete that education, transforming interstellar objects from rare oddities into familiar representatives of our galactic heritage. The wake-up call has been sounded. The era of routine interstellar visitor encounters is dawning, and ATLAS has shown us both the opportunities and the challenges that lie ahead in our expanding cosmic awareness. Part 15. Conclusion. The Cosmic Mirror. As ATLAS speeds through the final stages of its asteroid belt crossing, readying itself for its October encounter with our Sun, it brings with it more than just ancient ice and alien chemistry. This wanderer from the galactic depths has turned into a mirror in which we see our own place reflected in a universe far more peculiar and interconnected than earlier generations could have envisioned. Whether ATLAS withstands its solar encounter, gradually breaks apart under thermal pressure, or fragments spectacularly across our skies, it has already served its most crucial role as a cosmic messenger. Every spectrum, every brightness reading, every detail of its form captured by our telescopes contributes to a growing understanding of how materials move between stellar systems, taking with them the chemical signatures of distant worlds. The retrograde path that guides ATLAS straight through our solar system's most crowded areas is a reminder that cosmic traffic moves in all directions, on routes shaped by gravitational forces that work on galactic scales. The same orbital mechanics that control planetary motion around our Sun also shape the wandering journeys of objects scattered between the stars, leading to encounters like this one that connect stellar neighborhoods separated by light-years of space. Atlas's unique chemistry, the carbon dioxide-rich signature found by the James Webb Space Telescope, offers a tantalizing look into the formation conditions around stars very different from our own. The ratios of volatiles, the isotopic signatures, and the physical properties all point to protoplanetary environments where temperature gradients, radiation fields, and chemical compositions produced objects unlike anything in our local experience. There is a deep beauty in this ordinariness made extraordinary by distance and time. Atlas is not miraculous or supernatural. It is a natural result of stellar formation processes that occurred under slightly different conditions than those that shaped our own solar system. Yet those small differences, amplified over billions of years of evolution, have created an object that challenges our grasp of planetary formation and chemical evolution throughout the galaxy. The philosophical implications go beyond scientific discovery to questions of cosmic perspective and human importance. We are observers of processes that started when our galaxy was younger and very different from what it is today. The materials now sublimating from Atlas's nucleus were solidified when whole generations of stars were being born and dying in stellar nurseries we can hardly detect with our most powerful telescopes. Each photon of reflected sunlight, each spectral line revealing molecular composition, connects us directly to conditions that existed billions of years before our own planet was formed. We are literally looking back in time, not through telescopic observation of distant light sources, but through the direct analysis of materials that have kept the chemical signatures of ancient galactic environments. The technical accomplishments represented by the Atlas observations show how far human capabilities have come in understanding our cosmic surroundings. The coordination between space-based telescopes, ground-based observatories, and theoretical models has built an analytical framework that can pull detailed information from objects moving at hypervelocity through our solar system. We have become cosmic archaeologists, deciphering formation histories from materials that predate our existence by billions of years. Yet the encounter also underscores the vast areas of ignorance that still remain. Atlas is just one sample from the Milky Way's thick disk population, one data point in a distribution that includes billions of similar objects on their own wandering paths through interstellar space. The diversity of chemistry, composition, and formation history represented by the entire population is almost completely unknown. The practical consequences for future discoveries are equally significant. Atlas has served as a preview of the era that is coming, when the Vera C. Rubin Observatory will start detecting interstellar visitors routinely rather than by chance. The methods developed for quick characterization, the international coordination protocols, and the public communication strategies are all practice runs for managing a future where interstellar visitors are familiar instead of extraordinary. The safety concerns that always arise with any discussion of incoming cosmic objects have been definitively settled for Atlas. Its closest approach to Earth at 1.8 astronomical units puts it far beyond any chance of direct interaction with our planet. Even a complete fragmentation would create debris following the same hyperbolic path, carrying all pieces away from Earth rather than towards it. This safety allows for the luxury of pure scientific appreciation without the anxiety that comes with potentially hazardous objects. Atlas can be studied for what it teaches us about galactic evolution, planetary formation, and interstellar chemistry, free from the overlay of threat assessment that defines near-Earth object research. The cultural impact of Atlas goes beyond scientific publications to a broader human awareness of our place in cosmic time and space. The realization that our solar system gets regular visits from objects formed around other stars fundamentally alters our view of isolation and connection. We are not alone in the way that fictional stories often depict, but we are connected through material processes that operate on scales both intimate and immense. The dust that Atlas sheds as it nears our sun will join the zodiacal cloud that fills interplanetary space, mixing interstellar materials with the debris from our solar system's formation. Future spacecraft and perhaps future human explorers will encounter these particles without knowing their extraordinary origin. Interstellar chemistry will become a part of our local environment, indistinguishable from materials that never left our stellar neighborhood. In this way, Atlas represents both an arrival and a departure, a visit and an integration. The object itself will speed away from our sun on a modified but still hyperbolic trajectory, taking samples of our solar wind environment back into the galactic wilderness. But the materials it leaves behind, the gases and dust that make up its coma and tail, will stay with us, permanent additions to our local cosmic environment. The observational campaign is ongoing as Atlas approaches its solar encounter, but the most significant discoveries have already been made. We have confirmed that interstellar space holds a diverse population of objects, carrying chemistry from throughout our galaxy's history. We have shown that natural processes in foreign stellar environments can produce materials with properties that challenge our theoretical understanding. Most importantly, we have demonstrated that our solar system is not an isolated island, but a way station in a vast network of material exchange that connects all stellar systems across cosmic time. As Atlas fades from our telescopes, whether through survival and departure or through fragmentation and dispersal, it leaves behind a changed understanding of our place in the galactic community. We are citizens of a universe far more dynamic and interconnected than we previously imagined, participants in processes that link stellar formation throughout our region of the Milky Way. The ancient wanderer has delivered its message, written in the universal language of physics and chemistry. The translation is still in progress, but the essential meaning is already clear. We are not alone. We have never been alone. And the materials that constitute our world are part of exchanges that span the galaxy and bridge eons of cosmic time. The cosmic mirror reflects not isolation, but connection, not uniqueness, but participation in processes that extend from our local neighborhood to the most distant stars visible in our night sky. Atlas has shown us our reflection in that mirror, and the face looking back is both familiar and wonderfully strange, ancient and eternal, local and cosmic. The next visitor is already on its way, carrying fresh messages from stellar systems we will never see directly. The conversation continues, written in the eternal language of wandering worlds.